So, example 1, a basic Poisson introduction. It's adapted from this paper, Simmer our package, blah, blah, blah. You can actually get it here. It's really great. The only difference here, when I did it, I changed some of the variable names to kind of have a narrative. So the research question we're trying to answer with this data is, do prescription rates, so PR rate, at a certain hospital differ by day while controlling for doctor? So we want to model prescription counts for 10 days each across 3 doctors, so a total of 30 samples. So our model, glimmer, precision rate as a function of day with doctor in here as a random effect, Poisson distribution. So this is a random intercept model where each group, the doctor, has its own intercept, but the doctors share a common trend. So doctor is a random effect, and again, day is a fixed effect. Remember, we want to get data, create model, run model, and power curve. Okay, this is the R code for this. So you can use this if you'd like, copy and paste it into your R script editor of choice. I'm going to cut away here and actually show you this code as I run it on R Studio. We'll start by loading our packages, and making sure our working directory is to the right place. Okay, so for example 1, step 1, we'll get our data. We'll pull this in. Take a look at the data down here. We see we have 4 variables. We're not going to use cancer, but we will use day, doctor, and prescription rate. Step 2, we'll create a model. So we've seen this before, glimmer, rate as a function of day and doctor, and then we'll summarize after we run this model. Pops stuff out here. We see that day in this model is significant, and that the effect size for day is negative 0.11. So we can also view that on its own using this line of code here. Same thing. We can actually change the effect size if we want in our model. So let's change that to about half the size, because if this was, say, a pilot study, if we're doing a full study, we might expect a smaller effect size, so we'll want more samples. So now we'll go to step 3. We'll simulate power given a sample size of 10 per group. Okay, and this will start running. There are options in PowerSim to turn off this. I usually like to see this run so I know things are going on. This is going to take about a minute, so we're going to cut away and come back when it's done. We are back. It took about 2 minutes, and what this gives us after we simulate is our predicted power, which is 42%, and these are the confidence intervals, so not very good power. So we're going to extend the model to increase sample size to 20 per group. So we can create another model and then run PowerSim again. So as we let this run, we'll cut away. Okay, this time it took about the same length and much greater power, actually well above the 80% power that we would need. So we're going to move on to step 4 now. We're going to run a power curve to see if we can kind of figure out what the minimum sample size is, because 10 is too little, 20 is too much. So we're going to power curve our model 2, and then after that runs, we'll print it out and plot it. So this is going to take a while, so again, we'll cut away. We are back after 11 minutes, so you can see that power curve can take a significant amount of time. Here's the printed version where it shows power and then sample size, and then a very nice graph over here showing power and sample size for day. We went from, looks like 3 to 20. And this is sort of the 80% line we're trying to hit. So we increased sample size for day. We can also increase group size. So instead of having more days, maybe we could add more doctors. So we're going to create another model here and then run a power curve on that. So we're simulating here to take a look at that. We'll be back after the simulation. Okay, that took even longer, 13 minutes. But what we see here is that if we increase the number of doctors, of course, power goes up, and we have this nice threshold again. Now, we don't just need to stop at increasing doctors, so that group, or increasing samples. We could also like repeat samples, which is done by increasing size within group. So let's say we want to extend the model. We'll go back to model 1 with day and doctor and set that to 5. We can do that and then also run a power curve and actually set our own breaks. Instead of just like the 10 that it auto does, we can set our own 1 to 5. So let's run that. And again, this will take some time here, so we'll be back. Okay, a little shorter 6 minutes because we only had about half as many breaks, and we see that we get the nice graph here as well. All right, with that done, we'll cut back to the PowerPoint and briefly summarize the results. We're back here to the results. This just shows those graphs we created in our studio again. So what we saw for the first model, there was not enough power. For the second model, where we increased the number of days, was overkill. So then we went on to create these different power curves to find that sweet spot. So it looks like for when we increased day, that the minimum sample size that to get 80% was about 14 days. So that's for 14 days per 3 doctors. Now, if instead we increase the number of doctors, so the group size, we would need about 8 doctors to do that, each with 10 days. However, if we wanted to do like essentially repeats, like resampling, which may not be really appropriate here, but if we did that, we would need 3 repeats to get 80% power, and that would be 3 doctors over 10 days. And so what this kind of shows here, there are different ways to increase your sample size, either by increasing the number of groups, this is the number of days within groups, or both. And one way might be easier than another way. Maybe it's easier to just add days, or maybe it's easier to add doctors, or maybe you're constrained by both and just need to add repeats. So there we have it for our first example. All right, let's take a look at the second example. This is also from that paper in the appendix. The research question we're going to be asking is the incidence of CBPP. We've seen this data set before. This contagious bovine pleuropneumonia. Is it different across period or size? So we're going to model incidence across period and size while controlling for herds. That's our random effect. Here's our model here. So size will be a continuous predictor effect. Period is going to be a fixed effect. And then herd is a random effect. So again, get data, create model, run model, and power curve. Here is the R code. So now we will cut to our studio again to take a look at it in action. Okay, here we are in R. We'll start by getting the data. Since this CBPP data set is part of package simmer, we can just take a look at it. It's already loaded. See herd, incidence, side, and period. Next, we'll create a model with period only as a fixed effect. Herd is going to be random. And then we'll also run a likelihood ratio test. Okay, what we find here is that period looks like it's significant. Now let's add size over on the right side and run a z-test on that size. Okay, and what we find here, that size is not significant and it has a very small effect size, unsurprisingly. Alright, let's move on to simulating power. We're going to run power sim for the first model with period only. And since we have only 50 simulations, this should be rather quick. Yep, here we go. 50 simulations, and we find that, yeah, very, very high power. And then it gives us a warning that this might be observed power, so keep that in mind. So let's try the size model now. And once again, we're going to look at size. You see here that we have our model, and then our size is going to be what we're looking for. And yep, and what we get here for size is a very low power, so unsurprising. Now that we've ran that, let's change our, we know that there's very low effects, small effect size for size, so let's change it to make it bigger. So we can change the effect size in our second model so it's a little bit bigger. And then let's run a power simulation again. And after a couple seconds it should pop up here, and with that, yes, okay, so increasing effect size, unsurprisingly increase the power, but still not a lot. So what we're going to do here is run a power curve. So first, we're actually not doing a power curve. It's not really applicable here. What we're gonna do is just extend our herd, so double the number of herds to 30, and then run a power simulation with that to see if adding more herds will help. The reason why power curve is not applicable here is we're really just kind of, as we see these results down here, we see we're at 84% where we want it like to be, and since it's pretty much a little bit over 80, that's pretty much exactly the number that we want. We don't need to do it over a long stretch of time because we kind of already got what we wanted. So that's all it is to there. We will go back to the PowerPoint. To the results. So what we found for the period model, we had plenty of power. But if we added size model with the original effect size, there was a lot of power lacking, so we needed quite a bit more power. Now if we added a larger effect size, more power, but still needed more, so we tried to extend herds, which we did, and we got 80 to 84%. Now what I just showed you was 84, this is 80. That's because each simulation will be slightly different, so but they should be in the same ballpark. Now one thing to note, this effect size was, when I have ran it, it's quite a bit bigger than the appendix example if you take a look at that. Not really sure why, but that's just a bit of an aside here. Alright, with that we'll wrap up this and move on to the next example. So, simulation without data. So this is taken from this website here, where they show us we can simulate without any real data. So the question they pose is there a difference between a treatment and control for school children across classes? So the model they'll be creating is y, whatever our response variable is, treatment and time, and then the interaction of treatment and time, and then class as a random effect, and also ID, which is nested inside class. So we'll get data, create model, run model, and do power curve as always. So here is the R code. Quite a bit going on. There's a lot of data we need to create ourselves, and then a lot of work to do on the power curve, so I will switch over to the R and we'll take a look at that. Okay, here we are back in R. We're going to start by getting our data by making it. We will create 4 covariates: subject, class ID, time, and group, and then populate them so we have full data set. Then we'll get covariates, create a data frame, so we'll do that. And then we can see here's our different covariates. So we have ID, class, treatment, and time. You can see they are iterated as we would like for a total of 150 samples. Then we're going to create a intercept and slope for our fixed effects. So intervention, time, and then the 2 interaction terms. And then we're going to have random intercepts for participants clustered by class. So these are just vectors we've made up. And then we'll have a residual variance. And then to create the model, we're going to use this function called makeLimmer. So we have y, so function of treatment and time, so this will have the interaction as well. Our class with ID nested inside of it. Our fixed effect is that fixed we set up here. Our variance will be this random, and then sigma is RES, and then data is this covars. So this is how we create our model. We can do it here, and we can see that it's come out here. Now we'll simulate power for this model. So we'll run this here, and this is for time. So we're going to compare time. It's 100 simulation, so I'll take a little bit here, but it shouldn't be too long. Okay, there we go. And we see that we have 48% power, so this is underpowered. We're going to have to extend the model. First, let's take a look at treatment as well. So we've already looked at time. Similar sort of running time, I think. Okay, and we have a kind of a similarly rather low power. So let's go on to the power curve, which will do a lot of extension. So first, let's take a look at changing the effect size. So we're going to create a new model called model large, which will bump up the effect size to 2. And now let's take a look at that as well for the time variable. We're going to run this. So remember when we ran it up here, it was only about like in the 40s. Let's see how much that helps with our power, and yep, quite a bit higher, with above the range we need it to be for the minimum. So that's one thing we can do. We can also change the number of classes. We saw this in our first example. So we're going to extend it, and we're going to run simulation based on this extended. And yeah, it looks like that bumped up the power to pretty much overkill. So now we're going to do a power curve to see if we can find that sweet spot, that sweet good size that'll be right around 80. So this, I'm sure, is going to take a long time, so I'm going to pan away and we'll be back when it's done. Okay, we're back, and printing out the curve took 17 minutes, and we see that of our 10 points over on the graph here, looks like the numbers are going to be between 10 and 15. So Now what we can also do is change number within classes. So we can extend that. And we're going to need to go within class, treatment, and time. So we're going to extend the model. So we're going to extend that out. Now we're going to also run a power simulation on that. So we'll see you back here when these are all done. That only took a couple seconds with the power simulation. Now let's move on to a power curve where we set the breaks ourselves to 4 different breaks. Since we found that this extension gave us pretty good power, so we're going to go within these 4 segments of 5 to 20 in integrals of 5 to flesh out ideal sample size. Okay, we'll run this, and this should take a while. We'll see you back here. Finished up here, and we got a plot to our right side. You can see that, yep, once again, it falls between 15 and 20, that kind of 80% sweet spot. So we changed number of classes, number within classes. We, of course, can change both. So we'll make a final model to extend along class, and then extend within class, and we will run a power simulation and print out that final. Okay, and what we found here that, yep, if we ran both, we got a pretty decent power. All right, we'll turn back to the PowerPoint now. To summarize example 3, we found that for the base treatment model, there was not enough power, nor for the base time model. When we upped the effect size for treatment, we got enough power. And if we added more classes to the treatment model, we could get enough power by needing about 13 classes from looking at figure 1 here. So if we go from here, it's about, I think about 13. I think 12 might be a little bit too well, 12 or 13. And then for the treatment model, if we had more within classes, we also had enough power. Close this here. We would need about 15 students within each class. So we see right there. And then if we added more and more within class, we again got enough power. And again, if you run these yourselves, these specific power numbers will be mildly different depending on your simulation, but they should be within the same ballpark.